Good morning, friends from the floor and online. Here's today's HAESCO's first seminar in the year 2021. The seminar will begin in 5 minutes. Please be patient. Yeah, the show will be on later. Thank you.
Okay, good morning. Is everybody online can see me or hear me?
Yeah, clearly.
Well, it's the first time I'm moderator a hybrid seminar, so bear with me. And we are very lucky and happy to be here at the Polytechnic University. Thanks for the courtesy and great help of one of our speaker, Professor Eric Chang, making such a wonderful facility, and also the technical facility that allowing this to happen. We actually have a full house because of COVID restriction. The maximum we can have is only 20, and I believe we have a full house here. And my understanding from the registration is that we also has a very large crowd that have signed up for our seminar. And I'm particularly thankful to many of you from the North America that you are staying up late in the evening to attend our seminar. So on behalf of HAESCO, I thank you and hope that your time would be worth the while. Good morning again. I am Colin Tam, Chairman of HAESCO and the moderator for today. Now, first of all, it is my honor and pleasure to welcome you all to the first 2021 seminar of HAESCO and OSI Energy Efficiency Forum. And before I go any further, I would like to introduce our founding and now honorary chairman of HAESCO, Mr. Dominic Ying, who's also here. I also want to recognize our vice chairman, Mr. Patrick Ng, who's also here. At the same time, I want to recognize our honorable treasurer, Mr. Simon Cheung, who's very well represented by his assistant here, Amanda. I also want to recognize our honorable secretary, Dr. Ivan Lee, who's also here. By the way, Ivan is also a graduate of Polytechnic. Without them, we would. I also want to thank the board of directors of HAESCO, and I noticed that some of them are also here. Without them, we will not be able to carry on with our many events every year. During the past 3 and 4 years, HAESCO organized every year at least 4 professional seminars like this one, an annual conference, a factory visit, and we support the Eco Expo Asia conference in Hong Kong, as well as the MIECF conference in Macau. HAESCO also participated in the planning of these conferences. HAESCO was founded on 12 January 2008, more than a decade ago. It is the first Hong Kong Energy Efficiency Services Association. HAESCO aims to bring blue skies back to Hong Kong by saving energy. Its members include local and international energy service companies that specialize in helping factory and industrial facilities to upgrade production technologies and by reducing energy use and improve pollution control. This mission nowadays expands to the commercial and residential sector as well. Many of our current HAESCO members also involved in renewable energy, digitalization of the energy industry, carbon footprint reduction, and new energy such as hydrogen, which is the topic of today's seminar. This seminar is funded by the Clean Production Partnership Program of the Hong Kong Productivity Council. And Hong Kong Polytechnic University is a co-organizer with supporting organizations which include Hong Kong IE's Gas and Energy Division, the Institute of Mechanical Engineers, IPPF, IEEE, PES, PELS, IES, and IAS, and the Hong Kong Environmental Industry Association, the Hong Kong Green Strategy Alliances, the Hong Kong Fuel Cell and Hydrogen Energy Association, the Business Environmental Council, the Hong Kong International Smart City Research Institute, and GCSDGA. We will have three speakers today. Ms. Carrier Leon Zhao of the Lantau Group, Professor Eric Zhang of the Polytechnic University, and Mr. Albert Lau, the CEO of ePro Advanced Technologies. So now let's start it. Our first speaker is Ms. Zhao, ladies first, and she is currently in Shenzhen, so she will be joining us by Zoom. Carrier is a consultant at the Lantau Group. She had been involved in Lantau Group's commercial study on power and gas across several Southeast Asia countries, Thailand, Philippines, Vietnam, and Myanmar. More broadly, Li Yuan plays a key role supporting TLG's work in China, where she has been involved in renewable energy, energy storage, and power tariff forecast. She has also led on fuel price analysis and forecast at TLG. Prior to joining TLG, Li Yuan gained international experience in both mainland China and Saudi Arabia, working for a global consulting company, a diplomatic mission, and an energy think tank. Li Yuan holds a Master in International Relations from Jinan University and a graduate certificate focusing on energy, resources, and environment from the Johns Hopkins Nanjing Center for Chinese and American Studies. She is fluent in Mandarin and English. So without further ado, the floor is yours, Carrier.
Thank you so much, Holly. So you hear me and see me okay? Right, so next I will share my screen. So if the staff can share your screen, please. Thank you. Now I'm sharing my presentation in PDF. Yeah, so let me know if you have any issue to see that. Right, so today my presentation will focus on the hydrogen development in power and industrial sectors. So before we further talk about hydrogen, let me first briefly introduce the Lantau Group, which I'm working with. So the Lantau Group is a consulting firm that focuses on the energy sectors. And we have a strength in economic analysis and strategy consulting. And our footprint covers the multiple countries, starting from Southeast Asia and to north to China, South Asia, and south towards like Australia and New Zealand. Yeah, so we are focusing mostly on power and gas. And today's today's presentation, I will introduce hydrogen in 3 aspects. So first of all, so a brief introduction of hydrogen and its importance. And secondly, how can we transition to a green hydrogen production? And thirdly, so if the hydrogen cost is low enough, so except the current demand of hydrogen, what other sectors can we have further demand growth? For instance, like power sector and industrial sector. Right, let's start just from the introduction. So nowadays, the decarbonization is the trend and got the consensus of many countries in the world. And to achieve decarbonization, one important way is to use the renewable energy. However, the renewable energy has a nature of intermittent, so it needs some other technology to back it up to serve a very stable, serve as a very stable power supply. So battery is one of the means, and hydrogen is also another alternative to support, to bridge this gap and to support renewables. The reason is that hydrogen has its own advantages. For instance, it's very energy intensive by mass, and also it's very clean. And we'll talk about it further on this slide. And so we just said that on one hand, the hydrogen is a very high energy content per unit of weight. And so this is its merits. But on the other hand, it has a low energy content per volume. So it means that if hydrogen is in gaseous form, so its energy content is relatively low compared to other gaseous fuel. So as a result, it would be great that hydrogen can be stored in liquid form so that it's more energy intensive and can be used like in long haul vehicles. And another merit is that the use of hydrogen itself has no carbon emissions. However, if we have a look at the full life cycle hydrogen carbon emissions, we want to see from the production of the hydrogen. And this chart below shows that the different hydrogen production methods. So from left to right, it's more carbon intensive to less carbon intensive. And we can see some familiar name like gray hydrogen, which is made from like fossil fuel, like natural gas, and green hydrogen, which made of like renewables, electrolysis. And blue hydrogen is made of fossil fuel as well, but it adopts carbon capture and storage technologies so that it emits much less carbon to the atmosphere. So currently, hydrogen is most used for the industrial feedstock, as we can see on this chart. The blue bar represents refining, and this one in the yellow one in the middle represents ammonia and others. So most of industrial feedstock. And in the future, actually hydrogen can play a larger role, not only for industrial feedstock, but also in the energy system. It can support renewables to make even greater contribution. Yeah, for instance, it can address some critical energy challenges for some sectors. For instance, the transportation sector, especially the long haul one, which is hard to decarbonize. So hydrogen have the potential to play a role. And also hydrogen is very versatile. And we have mentioned that it can be used in different and can be used in different format of formations, for instance, in gaseous format, in liquid format, as well as hydrogen can be transferred to ammonia to start. Yeah. Right. So talking about the hydrogen production methods, there are mainly 3 categories of the production methods. So the traditional one is reforming, the steam methane reforming by using the fossil fuels, and also also hydrogen as a part of the chemical products mixed with other gas. And the cleanest one is electrolysis by renewables. Of course, electrolysis can also use great energy, great power, not necessarily renewable power. So from left to right, we can see the method is more and more emerging and advanced, but from right to left, it is more and more widely applied. And different methods just have different merits, pros and cons. For instance, the traditional one, by using fossil fuel, the reforming one, has stable production and is relatively cheap. For electrolysis, so this is its disadvantages. So at this moment, when renewable energy, the cost is still not fully competitive with fossil fuel. So the electrolysis cost is a bit high. However, when we talk about carbon emissions, so the reforming just lead to a lot of carbon emissions. And for the electrolysis, it depends on what kind of power sources it is using. So if it's using renewables, there's almost 0 emissions. So when we talk about electrolysis, we mean that so to break down for instance, the water molecule into hydrogen and oxygen just by means of electricity. And yeah, so the current most widely applied approach is the alkaline electrolysis cells. However, the proton exchange membrane electrolysis cell is more efficient, but currently the cost is high. Yeah. So nowadays, most of the hydrogen is produced by fossil fuels. As we see on this map, the left-hand side shows the supply source of the hydrogen, and the right-hand side shows the demand and for hydrogen. And natural gas, coal still account for the majority of the hydrogen production, and electricity is only accounting for a very small share today. And yeah, for the demand side of the hydrogen, mostly come from the industrial feedstock, and also a little bit from transportation system. But this is changing very fast as the hydrogen industry evolves itself. And this so a lot of hydrogen produced from fossil fuels will result in significant carbon emissions. So let's see a group of data. So on the left-hand side chart, we just ranked the carbon emissions for different countries and just regard the global total hydrogen production as a country. So imagine this is a country, and we just rank the total emissions just emitted from the hydrogen production. And it is actually ranked the 6th of the countries in the world. So it's almost like similar with the total emissions from Japan, all the industries, or Germany. So it's huge. And it's also, there's great potential to reduce this carbon emissions and to achieve Paris goals. And on the left-hand side chart, we can see like for different technologies, actually the carbon emissions intensity is very different. And we have said that for coal and for gas, the intensity is high, and for renewable, it's almost zero. And you may wonder why the coal power, so the hydrogen produced by electrolysis via coal power is even higher than the hydrogen produced directly by hard coal. So the reason is that, so during the coal power is generated and transmitted and distributed, there is power loss. So as a result, to generate the same kilogram of hydrogen, it requires more coal and resulted in more carbon emissions. Yeah, we talked about the importance of using green hydrogen. However, these days, the green hydrogen, the cost is still high. So we'll have a look at how can we reduce the total cost. So if we look at the components of the delivered hydrogen cost, we can break it down into the production cost, the storage and transportation cost, as well as the refuel cost. And in the chart below, we can see no matter for today's cost structure or for future cost structure under different power price scenario. So for electrolysis approach, the hydrogen production cost is always accounting for a greatest share of the hydrogen delivered cost. So we'll have a further analysis on the hydrogen production cost by electrolysis and see how we can reduce that cost. Yeah, so as we mentioned earlier, that nowadays the hydrogen produced by fossil fuels is relatively cheap than the hydrogen produced from renewable energy, nuclear, and solar. Just to make it a parallel, for instance, the coal gasification with CCS, the cost to produce hydrogen is around like $1.63 per kilogram. So it is equivalent to $77.1 per barrel. So today's crude oil price is just around this price range. So we can just understand this more in a wider context, that the 1.63 is like a parity of today's oil and gas price. So if renewable, if the green hydrogen want to be really cost competitive, there's still a long way to go. Yeah, so the gray bar shows the range of the cost, and the yellow dots shows the average of the cost. So let's have a look at how we can reduce the electrolysis, the hydrogen cost made by electrolysis. And yeah, so for this analysis, we mostly focus on the renewable hydrogen. So on the left-hand side chart, we just raise an example of the hydrogen made by offshore wind in Central Europe. So this is a kind of average renewable cost. This is not super low. But for the chart on the right-hand side, we just raise an example of the solar PV that's generated in Middle East, and we use the PV power to make hydrogen. So it's relatively low renewable cost even for today. And for the hydrogen production cost, we can break it down into three parts. So first of all, the capital cost, the capex, and this blue part, the capital cost, investment for like electrolyzer, and the energy cost. For instance, the renewable power cost, and other operation and maintenance cost is this yellow part. So today, these three parts in total will account for around $5.4 per kilogram of hydrogen. And so in 10 years, there is likely a trajectory that the total cost can be reduced to 2.3. And the greatest part of the decrease comes from the energy cost. which means that offshore wind cost has the potential to decrease sharply. And in contrast, on the right-hand side chart, in Middle East, where the energy cost is already relatively low, the greatest drop of the green hydrogen cost can come from the capital cost. For instance, the electrolyzer, when it has greater economy of scale, and it has the potential to decrease. So from these two charts, we kind of conclude that if we want to reduce the green hydrogen production cost, there are two means. One means is to reduce the renewable energy cost, and the other means is to reduce the electrolysis, the capital investment cost. Yeah, and we just did some sensitivity analysis on how this two cost reduction can affect the green hydrogen production cost. So these three charts have, so let's first see what's the difference between the three charts. So for the first chart is electrolyzer. CapEx is $750 per kilowatt. And the middle one is 500. And on the right-hand side is 250. So it's more and more cheaper in the future. And if we see under the same, we just control one ingredient. So make sure that the RE, LCOE is the same. For instance, we all look at the 100 so the renewable cost is $100 per megawatt hour. So for the 750 case, electrolyzer CapEx case, the hydrogen cost is starting from around like 10 and ending at around like 6.5. But as the electrolyzer CapEx is reducing, this line is also moving down. Yeah, just starting from 9 to 6, and even reducing the hydrogen production cost is even decreasing. And here the hydrogen cost decrease with the load factor of hydrogen production is increasing. So what does it mean by load factor? So it means that how much is the utilization hour of the hydrogen production. For instance, in 1 year, there is 8,760 days. So if I turn on the hydrogen production electrolyzer for, let's say, 4,030 and 300 hours, so its utilization rate or load factor is around 50%. So the more that I turn on the hydrogen production, the lower the cost it will be, because the fixed cost will be shared by each unit of hydrogen that's generating. Right, so we have analyzed these three charts horizontally. So let's have a look at one chart, let's say the chart in the middle, just vertically, and see how the renewable costs can affect the hydrogen production. So when the renewable cost is very high, for instance, the $100 per megawatt hour, the hydrogen cost is very high. Let's say if one day the renewable cost is widely applied in the world and costs as around $20 per megawatt hour, the hydrogen cost will greatly reduce. Let's see this brown line in the middle. And when the hydrogen load factor, the utilization rate is high enough, it's very competitive with the traditional ways like steam methane reforming. And yeah, and in the future days, when the electrolyzer CapEx is even lower, the cost by using green hydrogen can be even lower than the fossil fuel. So how can we achieve the decrease of capital cost of electrolyzer? We believe that it can be achieved by economical scale and also the learning rate. And so in this chart, we show how the water electrolysis capacity developed in the past, and it is expected to develop in the future. And although we can find that the electrolysis capacity is increasing very fast in this small chart. Actually, in this greater chart, it's only very small in the beginning. So that's how we imagine in the future there is like booming water electrolysis capacity. And with the capacity growth, there is learning rate for electrolysis. For instance, so in this chart, we just like listed different technologies and see how their trace of cost reduction can be happen as the cumulative production is there. For instance, let's just have a look at this onshore wind learning rate. So this is the data is collected from 2010 to 2020, and the projection, is like the production is increasing from the 1 million magnitude to 10 million magnitude, and the cost has decreased rapidly. And for the water electrolysis, we just expect it can have some similar, although maybe as high learning rate as solar and onshore wind. So as the cumulative production of the like electrolyzers or fuel cells is increasing, we expect that the capex cost will also decrease. So that's how we imagine with the future cost reduction. So on one hand, it's the electrolyzer will be, the size of the electrolyzer will be larger and larger. And on the other hand, the different companies will compete with each other. So this will also push the technology to reduce this cost. So imagine one day when the green hydrogen cost is already very low. So the application can be developed from the current industrial feedstock to many other sectors. Currently we are at here, the feedstocks for industry, for instance, the ammonia, the methanol we have mentioned. And in the future, and in the near future, we already see some applications in the transportation field. For instance, the material handling vehicles, the heavy duty vehicles, which really require very long haul and a very long duration of the energy. And on the left-hand side, in the power system, hydrogen can also play a very important role. For instance, as a backup energy and as a storage medium to store storage for long duration energy, which means it can save a lot of energy and can release for a very long time, like days or even weeks. The hydrogen also has the potential to serve as the residential and the commercial buildings fuels. For instance, it can be blended into the just natural gas grid and to replace part of the natural gas so that the total emission will decrease. So this chart about hydrogen console just showed us, so for different applications of hydrogen, so how fast it can be cost competitive. So this solid line shows that the hydrogen is only competitive in optimal conditions, and this dotted line shows that hydrogen is competitive in average conditions. And yeah, so for the industrial feedstock, so hydrogen is already very competitive in different applications like ammonia, like refining. And in some sectors, the hydrogen is also going to be competitive soon. For instance, the backup generation and the simple cycle turbine. When we said soon, we mean that by 2030, so it's like in a decade. And also in the transportation system, like heavy duty trucks, like coach, there are also chances that the hydrogen vehicles can be cost competitive in years. So let's first have a look at the transportation system. And in this slide, we just show how the FCEVs, fuel cell electric vehicles, and the refueling station is developing in China. So on the two parts, on the first half of this slide, we show that the historical FCE, the fuel cell EV growth, and the future expectation. So the fuel cell electric vehicles in China has seen steady growth and until 2020. And there are two reasons. One, that 2020 fuel cell electric vehicle sales and production was halved. The one reason is during the COVID-19, the market environment is not good. And the second reason is that the subsidy policy for fuel cell electric vehicles have been shifted to another policy that will only support the city groups or regions to develop fuel cell electric vehicles after it has already built a lot of fuel cell electric vehicles and is qualified. So that's a kind of incentive afterwards. So the transition of policy just also contribute to this decrease of the annual production and sales. However, in the long term, the fuel cell electric vehicle is very promising and promising to account for a greater share of the new energy vehicle market, according to the forecast of the China EV 100. And on the second half of this chart, we see the incremental refueling station in China is also increasing annually, and also the forecast of this market is very promising. And all this development in the hydrogen application in the transportation system is like supported by different policies in China. For instance, no matter the national level subsidy policies and as well as the provincial level support policies. And this also happened in different countries like Japan, Germany, Korea, Saudi Arabia, all have supportive policies for fuel cell and hydrogen strategy. And most of them also have a stress on the transportation system. And we believe that the reason why the policy has a focus and emphasis on the transportation system is that this sector, especially for the heavy duty, is very hard to decarbonize in other ways. For instance, if it really requires a lot of energy, and so probably it's the other technologies is harder to support compared to hydrogen. And after seeing the transportation industry, we'll have a look at the power system and how the hydrogen can support the power system. And at the very beginning, we said that hydrogen has the potential to help with the renewables, to support it, to coordinate with renewables, and to generate more stable power to the grid. And compared to the battery, compared to renewable plus battery, renewable plus hydrogen has its own pros and cons. Although hydrogen, renewable plus hydrogen is also feasible, it is not widely applied as renewable plus battery. There are only some pilots around the world. And in terms of the advantage, so the battery storage is like react very quickly, can ramp up and down very quickly. However, the storage hour can be just last for maybe 1 hour, 2 hours, 3 hours. And for hydrogen, it has the potential to provide the long duration storage, for instance, for days or even weeks. And in terms of the cost, although the battery cost is high, but it's like quickly decreasing. But at this moment, for renewable plus hydrogen is it's not very economic, and it, remember what we have said, it depends on the reduction of a renewable power cost and the reduction of the high electrolysis cost. And in terms of the emissions, and these two technologies are all of almost zero emissions. And if we compare the renewable plus the power to like different storage technologies on the left-hand side chart, we just see different technology of storage have different merits and different characteristics. For instance, the battery, the largest one we see on the bottom left, they have a relatively shorter duration, and on this y-axis is like storage time, and this x-axis is how much power it stores in energy storage project. So for batteries, it's generally lasts for shorter hours, like minutes to hours, and it's a relatively small scale, like from kilowatt to megawatts. However, for chemical storage like hydrogen, like ammonia, its storage time is longer. For instance, like from hours, days to weeks, or even weeks. And as a result, its storage size, the project size will be larger. And let's imagine one day the green hydrogen cost is very low, and there are some application scenarios that the hydrogen or ammonia storage can play a greater role. For instance, in the storage can help to store some hydropower in wet season and release the power in dry season. For countries like Vietnam, where it has really a lot of hydropower, and in the dry season, although the power systems do have the capacity, but it cannot generate power. The hydropower capacity cannot generate power in the dry season. So at that time, it has the risk to face some like power shortage. So if we can storage the power into like chemical methane or hydrogen or ammonia storage and release that in the dry season, so it will help to reduce the power shortage and also reduce the need for building new fossil fuel plants for the dry season. And also secondly, the hydrogen storage can help to store power in mild season, which means that it's like spring or autumn season, and release the power in cold winter or very warm summer time. For instance, in China now, there are multiple provinces like Guangdong province that is facing power shortage because on one hand, the weather is very warm and the air conditioner load is very high. So as a result, the power is not enough, and some industrial or commercial sectors will be affected. Their demand will be affected. Let's say if we can storage power in mild season and release that in very warm season, this can potentially also reduce the power shortage. And thirdly, the hydrogen storage and ammonia storage can be storage power when the commodity price or power price is very low, and release the power when the price is high. And we know that the nature of electricity is that it has to be used immediately, or else it have to be storage somewhere. And if the electricity can be storage in large scale, then the nature of electricity will be more and more like the nature of commodity, because the commodity like gas, coal, oil, it can be storage. And so when the price is low, like during the COVID time, like China storage a lot of crude oil. And let's say if this can also happen to electricity, when the price is low, so we storage electricity in hydrogen or ammonia and release the power when the price is high. So it can also be helpful for the power system to just hedge the risk of great power price fluctuations. So the hydrogen, if we have talked about the cost of hydrogen production, and now we have a look at the hydrogen storage. Because the hydrogen, the boiling point is very low. It's like minus 252 Celsius degree. So it means that it's very harsh condition to storage that, and it's very costly. However, if the hydrogen is stored in the ammonia form, and ammonia has a higher boiling point of minus 33 degree, so it can be easier storage and can have a relatively lower cost. So in the application, it's more economic choice. And how ammonia is using in the power storage system. For instance, it can be used in the fuel cell to by using hydrogen and by using power and the nitrogen to produce ammonia, and can be used as fertilizer. It can be used as in the power plants, and also can be used to produce hydrogen and used in the fuel cell vehicles. So it's very versatile. And another application of hydrogen can be the hydrogen to be used in the fuel turbines, like gas turbine. So as long as the carbon price is high enough in the future, like there are a chance that the hydrogen can be cost competitive with the gas turbine and can replace the gas turbine just by using the otherwise curtailed renewables. Right, so let's have a summary of what we have talked about. Firstly, the hydrogen has its merits. It have high energy content per unit, and it's clean and emits no carbon emissions as long as the production life is clean as well by using renewables. And secondly, to reduce the green hydrogen cost, we can achieve that by reducing the renewable production cost. And we can also achieve that by reducing the capital cost of the electrolyzer to break down the water into hydrogen and oxygen. And thirdly, we talk about the application of hydrogen is very diverse, from the industrial feedstock to transportation to power system and even to industrial fuels. And we'll very look forward to that day that the hydrogen will play a larger role in the energy world. And thank you so much.
Thank you, Claire. Claire worked for the Lantau Group, which is headquartered in Hong Kong. And my understanding is that Claire also have a lot of help from all her colleagues in preparing for this presentation. And you can see the acknowledgement of all the other colleagues of her that contribute to this wonderful presentation. We will have a panel discussion after the other two speakers, and you can hold your questions. But in the meantime, You can also, if you want to, send the question to the organizer, and I would make sure that you get a chance to ask that. Or you can, right, for those who are physically in this room, all you have to do is raise the hand and you get a chance to ask the question. Not right now, Sarah. Okay, without further ado, it was my great pleasure to introduce our second speaker, which is Professor Eric Chen of a Polytechnic University. Professor Chen obtained his Bachelor degree of Science and PhD degrees both from the University of Bath in England in 1987 and 1990, respectively. Before he joined the Hong Kong Polytechnic University in 1997, he was Locus Aerospace, United Kingdom, as a principal engineer and led a number of power electronics and aerospace projects. By the way, Bath University was one of my candidate university where I want to apply to, but they didn't accept me, so I wind up in Salford University up north, near Manchester. Professor Chen's research interests include power distribution, power security, power electronics, motor drive, electromagnetic interference, electric vehicle, battery management, and energy saving. Dr. Chen received the IEE Sebastian Z.D. Ferretti Premium Award in 1995, the Outstanding Consultancy Award in year 2000, the Faculty Merit Award for Best Teaching in 2003 from the Hong Kong Polytechnic University, the Faculty Engineering, Industrial and Engineering Service Grant Achievement Award in 2006, the Brussels Inno Energy Gold Medal with mentioned in 2007, and the Consumer Product Design Award in 2008. Professor Chen must be very, very busy in receiving awards. The Electric Vehicle Team Merit Award of the faculty in 2009 and Silver Medal for contribution of solar air conditioning for vehicle at the Geneva Invention Expo in 2011, as well as Echo Star Award in year 2012, and gold prize in supercapacitor at Seoul, and silver medal in all electric anti-lock braking system in Geneva 2021, which is this year. His research interests are all aspects of power electronics and electronic vehicles. Professor Chan is a chartered engineer and a fellow of Hong Kong IE, IEEE, and IET. And his title for discussion today would be From Ammonia Powered Fuel Cell to Electric Vehicles. Professor Chen, the floor is yours.
Thank you, Chairman. And so today you just briefly to discuss some project we've been doing on electric vehicle, so they can understand briefly about what product you have been working on. So the content of my work I'm going to present today will be mainly on electric vehicle. We also discuss some briefly what we did on different kind of EV components. We also try to work on some energy storage and fuel cell, and mainly about ammonium fuel cell vehicle. That's the key topic which we're going to show you. I think we all know that about the recent development on EV. So that mainly will be some, yeah. So mainly about a lot of the new policy from different countries have been working on this area. In Hong Kong, 2035, we're going to stop issuing the petrol vehicle license. So all the other countries will be in similar year, either within 5 or 10 years, then we have something happen all over the world. So that's to say we need to do something seriously now in order to promote the electric vehicle. Of course, we have been using the battery vehicle for many, many years. The battery may not be a good solution because we all know that the battery are not the issue, like how to recycle them, and a lot of the carbon footprint in the battery, we do need to take care of them. So today we're going to show you some research work we have been doing. For example, like some of the smart power distribution we can be used in electric vehicle. We're also looking into some four-wheel drive and some beautiful EV component like how to control the torque and how to look into the anti-lock braking system and supercapacitor. Supercapacitor is one of the good things we try to work on how to store the energy much better than battery vehicles. We're also working on different kind of the fuel cell, like aluminum fuel cell. We also look into the battery management system, how to manage a battery. Because in EV, there's so many different kind of battery. So how we control them, we're talking about more than hundreds of the battery all connected in series or in parallel. So how we produce all of them. And in the area we working on with the solar air conditioning system, we put in a solar panel on vehicle, make use of the solar panel in order to provide secondary power for the vehicle. That's another way we can work on. So the technology we are working on mainly about different kind of the technique like power electronics. The meaning for power electronics mainly to use electronic to control the power. No matter what kind of power, large power or small power, we can also use it to control the energy transfer. And then we're using other technology like the finite element, motor technique, and high frequency power conversion and battery technologies. So here we can see different type of the EV development recently we are working on. So for the top here, you can see some golf car and also the portable brand name called the My Car, which we developed over 20 years. So you can also have some student project like this kind of the solar vehicle, just look like satellite. We can able to control the panel and extend them to different kind of size. So like this vehicle, the power level roughly about 1.5 kilowatt power. The white one roughly about 750 watt of power. So here you can see other solar vehicle. For example, like this is a Coca-Cola vehicle. The power level roughly about 750 watt of power. And then the other vehicle, like the AA vehicle, we're using them in the airport. Other vehicle, like the minibus, this one, you guess what kind of power level? About 1.3 kW of power level. We also a taxi as well. So this is not the main power for the vehicle because we know that solar panel cannot provide the key power for the vehicle, but only a portion of power. And this is something we can work on so that we can provide a portion of power to assist the renewable energy for vehicle. So here another example, like some lorry, private car, and other minibus of the development. Oh, sorry. Oh, one button. So here is my team. We work on different vehicles. Like this one of the vehicle, we go for a competition about 5 years ago. So now that I want to talk about different kind of EV technology. Like this one is called the linear compressor technology. It's actually based on linear motor. So this linear motor, actually, we are using a kind of the coil which only control the linear motion of the motor. So in this case, you can see that by using this method, we are not using a rotational motor. We are using a linear motor. You see a rotation motor not able to provide the linear power that good. So in this case, we have direct drive for the linear motor. So this kind of application, we can use them for example, like a compressor, air compressor, like the air conditioning system, can also use them for active suspension. The key thing is this development, we are not using PM motor. The thing is, we have been talking about PM motor per magnet for a long time, but the PM motor do have an issue about the magnet. The magnet is expensive, yet based on the rare earth material. So for this kind of motor, we're using a technology called the reduction technology, which is able to provide the same kind of the operation, but much cheaper and higher dynamic performance. So like here, you can see that here, this active suspension system, we're able to provide a linear motion by using this kind of the stator and translator technology. And then we don't have to use the PM technology. In this case, the power level much higher and much lower cost. Only can see that in here, we're only using silicon iron and copper winding to do the jobs. Another technology we try to develop to you will be so-called the e-mill motor. So e-mill motor, you can see here, the motor actually integrate together with the wheel. So you can see here, we got a number of winding here. Each winding provide a portion of the torque. So that to say, we don't need to have all the winding operate. In case one winding broken, just in case, the other 3 winding can also operate. So that means you can have a 4 times a torque fault tolerance. So this motor, we are using 4 sets of the coil for each wheel. So in this case, we are able to provide 4 times torque fault tolerance. The good thing is all the motor are integrated inside the wheel. So in this case, you can see that the vehicle will be much cleaner, much easier to design. We have no gearbox, no clutch, no transmission, no shaft. So vehicle will be quite easy to design. Inside the vehicle, we can have a much more space than usual. All the power energized from the wheel. So in this case, the future vehicle able to provide the so-called skid steering. That is to say, we're only using differential speed to control the steering. Another technology we try to do would be so-called energy storage using special package called the body integrated supercapacitor. So this job will be, because for vehicle, we got a lot of the room inside the package, like the door, wing, the roof. All this we can integrate with the supercapacitor. So any amount of component can become the energy storage. You can see that using this method, you can save a lot of the compartment. We don't need to have a square box to contain all the battery or supercapacitor. So in this case, they can be much better manage the package. For example, like in this vehicle, we're using the roof, the door, the wing to become our energy storage. So you can see that in the future, if we want to construct something so-called the configurable EV technology, that means to change the shape of the EV. Each of the component will be their own energy storage. So in this case, it's much better to manage the vehicle because the motion control energy storage can be any portion of the vehicle. We don't need to confine everything into a same location. So in this case, the vehicle will have much more flexibility to do different kind of the management. Another technology we are working on so-called ABS, anti-lock braking system. So we have been working on ABS for a long time, but ABS usually controlled by a field patent. So that means they're usually quite expensive. And however, today we are not using hydraulic system for ABS. For most of vehicle, 90% are using hydraulic system. Why is that? Because it has been using for a long time. But hydraulic is a problem because you may have leakage. We don't like the hydraulic, which is not pure electric. Even though we put a motor called hydraulic, still hydraulic system, so they're not that marvelous. So now then we are using a force motor, with a high power force motor to work on the braking system. Because we're using force motor, the force is really high. A small motor, we are able to provide tons of the force. And the speed is so much faster than hydraulic system, 100 times faster. So we can able to perform ABS really quickly. So what we have been doing will be try to calibrate the ABS into optimum frictional position. So that's usually we produce the slip into around this position, the optimal position, then we can produce the ABS technology. Another technology, now we go back to our real topic about the ammonia. So ammonia fuel cell, and many other fuel cells have been talked about for many years. So how do we go for that? We like ammonia, mainly because it's zero carbon. All the other fuel, to do the fuel cell, for example, like the methane, even the alcohol, still based on some C. So once you convert any fuel into hydrogen, we do have the C, like the CO2 production, we don't quite like that. So we are thinking about how the future fuel cell will look like in order to eliminate all the carbon carrier. So if you look into the energy storage, like here, there's many different kinds of energy storage, can be used for building, can be used for vehicle. So you can see here, on this left-hand side, we have a lot of the classical energy storage based on electrical mean. For example, like you can see we have different battery here, like the lithium-ion battery, fuel cell, even the conventional lead-acid battery have been using long time because of red dot battery as well. And then we also have much higher speed kind of the energy storage, so-called the electrostatic one. The electrostatic one, actually you can see that in here, we have this inductor, supercapacitor, all these things are much faster speed for energy storage or energy processing. The other thing, like the compressor air, fill, all these areas slightly higher and energy storage level, but they usually use it for bigger energy storage, like in a building, maybe city energy storage. So for electric vehicle, we mainly focus on these two areas. Firstly, we look at other energy storage, like the aluminum and the zinc. So we've been thinking about why don't we use aluminum or zinc as a fuel cell? Because this is also another good fuel cell we can use. One thing is we look at the price for the last many years, for the last 5 years, the aluminum or the zinc actually is relatively quite stable as compared to other metal for the last 5 years. And also, if we look at the production for the metal, I think the aluminum will be number 3, sometimes number 2, depending on different years, and zinc will number 6. Lithium 21, but last few years when I do the research around that, lithium will be 27. So recently be getting higher production mainly about the demand. But still you can see that to compare to all the other metal production, lithium is still expensive because the content in our resources in the mine. But if you look at the energy content, then you can see that aluminum 1 kilogram can produce 8 kilowatt hour. So that's quite a big number as compared to the battery. You know, the battery 1 kilogram for the lithium iron phosphate battery is roughly about 0.2. And then zinc will be 1.37. And the world production is quite big. So that's why we may need to think about using aluminum and zinc as a fuel cell with one of the alternative. And then we look at other metal price, like the cobalt and the lithium. So these are two main material we try to work on the battery. And then we can see the price for cobalt actually have a big variation. Although last couple of years it's getting cheaper because the demand, so that's why the manufacturing technology getting better, so getting much cheaper. But you can see a trend now is maybe going up in next few years because cobalt is still quite rare in terms of the production. And the lithium, another thing, have been go up really rapidly, but last few years, the price go down mainly about the demand, the manufacturing demand. So that's why it's getting cheaper. But we still do see a trend, it's getting high and high up because of too much demand. You can see that all the renewable energy need battery, even the EV, we need battery. So we have not quite sure about the future for lithium or cobalt. It may getting high and high up, maybe after 10 years, 20 years, become too expensive, it's not affordable to use battery. So we do need to think about alternative energy storage system. So of course, if you look into zinc air, it's one of the very promising fuel cell technology. I think we all learned about this equation in the high school about how we process the zinc air. The good thing of this energy storage will be using zinc as the energy source to provide the energy. So in this case, based on this red dot equation, we can able to provide the electricity. The good thing will be the commercial zinc air, we can able to provide more than 200 WH per kilogram, which it will be really much equivalent to the best lithium-ion battery. Reliability is good. Nighttime is also good as well. You also have a lot of the content in the earth. So recyclable. So that's why it's so far so good. We think zinc air will be one of the good fuel cell technology we can use. Another one will be aluminum. Aluminum, we can see that the energy content also quite high. At the moment, we go up to 300 WH. That number will be much better than a lot of the lithium iron phosphate battery. And this number, we still able to go up as well. Why is that? Because if you look at the theoretical maximum will be 8 kilowatt hour per kilogram. We're only using a portion. So we believe if you do more research further, we're able to extend this kind of energy content. Of course, aluminum become aluminum oxide or hydroxide. So for manufacturing process, this can be very easily to be recycled. So anything aluminum, after we produce the electricity, it can become hydroxide, but we can easily convert it back. And also hydroxide, actually we have a lot of the application not really need to convert back. For example, like we got the building material and also medical material, we can actually use hydroxide. So that's why we do have a lot of opportunity how to use them directly instead only think about the lithium iron phosphate battery or the other NMC battery. So how to use them? We just replace the aluminum. After we finish them, we become aluminum oxide. So we replace the oxide with the new aluminum. So in this case, this kind of fuel cell, we're using metal as a fuel instead of using hydrogen or other fuel. So there's another alternative we have been thinking. So you can look at all the different kind of energy storage. So this table gives you briefly about different kind of the comparison. So you can see that in here, the battery, of course, the efficiency is really good. Usually go up to 99%, really good performance. Of course, the energy storage depends on different type of battery. We can have a 30 to 300. 30 probably will be lead acid. 300 will be something like MNC battery, the best MNC battery. Supercapacitor, we've been using it. It's really good because the power level is much higher power level. If you want to have a really rapid, ultra fast of charging, we may think about to use this kind of the supercapacitor. But the thing is, the density will be much lower compared to battery, so we don't afford to have too much supercapacitor. We only use a really small portion, usually about 5% or 2%, because too expensive. Supercapacitor, we've been talking about it for a long time. It basically mainly based on the inductor to energy storage. But the thing is, supercapacitor, that means you need to maintain the low temperature. For example, like even the high temperature supercapacitor, you have to use minus 200 and something degree. That will be too much. And then the cost may not be so favorable. And flywheel, we've been using it mainly for building, but if you want to use them for electric vehicle, it will be troublesome. The other energy storage, like the fuel pump, that mainly for large power plant of the energy storage system. We can use them, and you can also see that the cost usually quite low as well. But however, we need a big investment. Fuel cell is the topic we have been talking about now. So efficiency still kind of thing need to be improved. The thing is, most of fuel cell, the efficiency only between 33 to 75, like all the fuel cell we talking about today. So that's why we still have room for improvement. Another technology we're thinking about is sort of the red dot battery, or we call them flow battery. Actually, this one, we are using the electrolyte as an energy storage. Once we charge up, the electrolyte will be energy source. We can transport the electrolyte to another battery. So that's to say in the future, if you want to fuel in the vehicle, charge the vehicle, we can only replace with the electrolyte, just like the petrol station. Instead using petrol, we are now using this electrolyte to do the jobs. And efficiency still some improvement. The best we can get from the market will be 85%, like the red dot battery, using the different. We have about 3 different types of popular fallback battery. Most of them can now go up to 85. In the laboratory, we can go up to about 95. So per commercial, roughly about 85. Another thing we look into will be about the nighttime. That will be really important. For the nighttime, we can see that The battery lifetime vary depending on which one. Some poor battery, like the lead acid one, can only have 100 cycle. But if you go for some good battery, you can also go to 10,000 cycle, like the LTO battery. And supercapacitors usually have a really good life cycle, something like even the 1 million times also become feasible. The other will be really much moderate, it's not really have a high lifetime. So that's why when you're looking into the fuel cell technology, today, most of fuel cell life cycle, something like 5,000 is not surprising, mainly about the membrane, for example, like PEM membrane, still quite expensive, still have a lifetime problem. So if you look at another thing about the fuel, if you look into the lithium iron phosphate, you can see that in the periodic table with group 1, so really active material. So we can see that the nighttime or the active thing or the dangerous will be something we need to concern. But however, if you look into the other metal, like the aluminum and zinc, they usually quite stable in terms of the usage. If you put them into the atmosphere, they are quite stable. So that's why I'm thinking about, shall we use the lithium as the key energy storage? Because eventually we can think about will be a safety concern. For EV application, we do think about safety will be most important. So that's why another option will be, we may need to think about aluminum or zinc as a fuel cell. That will be one of the future we like to work at. And hydrogen fuel cell, of course, is one of the key development for the last many years. So people like to use hydrogen fuel cell because, firstly, because of low side product, no CO2 for production, and also really mature technology. We've been using hydrogen fuel cell for hundreds of years. So we are really confident to use them. But however, the PEM membrane, for total exchange membrane, still have a lot of research work to do. The nighttime, the cost is something we need to work on. So, and also using hydrogen. Hydrogen has been all know that all the speaker for our technology. Then you can see that we usually try to use up to 700 bar to do the job. So that means this technology already really mature. But you can see that if you want to put them into electric vehicle will be one of the concern. You're putting the storage tank for 700 bar compared to 1 bar here. So how do you change the tank? How do you refill them will be one of the safety concern. Another thing will be about the vehicle. If you're putting a 700 bar of all the vehicle on the road, you go through a tunnel, go through a bridge, in case anything happen, will be an issue as well. I think the fire service department do not allow that. About 20 years ago, we tried to promote new project of this hydrogen fuel cell into the vehicle, but the fire department stopped it. Why is that? Because we don't allow that vehicle to go to the tunnel, go to the bridge, in case anything happens. For example, in Hong Kong, the cross harbor tunnel will be explosion. I think will be a big issue. Even though 1 out of 1 million still a big issue as well. So that's why this kind of project, we need to think about alternative fuel. We cannot only rely on hydrogen for transportation. We need to think about more safety method to do the jobs. So now then, we think about aluminum. Aluminum is another alternative. As you can see from previous speaker, we do have a lot of advantage to use aluminum. One thing will be aluminum will be widely available. It's not expensive. For example, like in the landfill or fertilizer, this kind of production, we can easily produce the ammonia. Ammonia is NH3, so you got one N and 3 H. So in theory, one molecule of this will have more energy, more hydrogen compared to hydrogen gas. So for same kind of the number of mole. And it's really a zero carbon fuel, low carbon at all. So when you use ammonia as your fuel, for example, even to burn the ammonia or use them for fuel cell, whatever, you don't have any carbon as a side product. So that's why we like it. Safe, really safe. Hydrogen, of course, still safe and not poisonous. But however, hydrogen is easy. You cannot smell it, even though you trap in one of the room. For example, like in this room, if you do have some hydrogen trap, maybe in one of the corner there, you may not aware of it. So in case any fire, they get explosion. So that's something you got to be really careful about it. But ammonia can smell it, although it's poisonous, but the poisonous level is not as high all the other gases. So that's why in a way it could be one of the choice. Rather than using hydrogen, we may think about the ammonia. So hydrogen economy is now being used to today, but we are thinking ammonia will be one thing we can support the hydrogen economy, maybe one of the economy for tomorrow as well. So here looking into different kind of the hydrogen carrier about the energy content comparison. So there's a many way we can use hydrogen, but this table shows us if we using the compressed hydrogen like the 700 bar one, then the energy content will be 120 megajoule per kilogram. You can see that 3.6 megajoule equivalent to 1 kilowatt hour. So you can see that in here, how much kilowatt hour we can per kilogram. And then if you go for liquid hydrogen as well, all the technology is good, but however, I can see that this quite a big investment for all the facility. As I mentioned before, if you want to use them for electric vehicle, this kind of the compressed hydrogen to use in EV was something we need to be really careful to handle them. If you look at the ammonia, ammonia is much easier to become liquefied, only about less than 10 bar, we can do the job. So that is to say much easier to handle. The energy content of per kilogram is not as good as hydrogen, but in terms of per unit cubic meter, they are really compatible, even better. So that means for same kind of the volume, physical size, we're able to get more energy from ammonia. But of course, the weight would be not compatible to hydrogen because you know hydrogen is the atomic number is number 1. So that's why we cannot compare with them, but two will be really good candidate for this. You try to compare to other natural gas or methanol, so you can see that they are really much compatible. So that's why ammonia could be one of the good choice for the future energy carrier. Yeah. Storage temperature. The thing is -24 when you liquefy, when you reduce the temperature, become liquid. Ammonia really easy to become liquid at roughly about -34. But if you pressurize them, even the room temperature, pressurize them to 8 bar, then you can able to become ammonia storage. So it depends on how you manage that. So this have two meaning there. So that's why we try to develop a vehicle using ammonia. So ammonia, what we're trying to do, we have the ammonia as a fuel, and then we use a cracker to crack them into hydrogen. So hydrogen, we just go for the normal process as a hydrogen fuel cell. So this part will be conventional fuel cell technology. We're still using a fuel cell because fuel cell is one of the way we have been using all the time, really mature. Ammonia cannot go directly to the fuel cell. So the cracker will be one of the things to transfer ammonia into this vehicle. The other part, like the energy storage, we do need to have temporary energy storage, like this kind of the small hydrogen tank or a battery. Why we need to still use battery? Because for power regeneration, when the motor is going down the hill or decelerate, this energy can be returned back to the battery. So that's why much more effective. Fuel cell itself cannot do the power regeneration. So that's why we have to use some energy storage. So you can see that ammonia, the size is quite small as compared to from the previous table. You can see that the physical size compatible to other fuel like the methanol. So that means in the future, we can put 10, the 10 will be only less than 10 bar. So much easier to handle. So in the future petrol station, we can just fill in of the liquefied ammonia or exchange with the 10, then that will do the job. So that's why this technology, we can able to have a continuous extend the range for the electric vehicle, but replacing the storage tank will be much easier to do the job. So that's the design now. So what we're trying to do, the whole vehicle, we go to a liquefied ammonia, pass through a cracker, filter it to remove all the remaining NH3 because fuel cell is not really happy about the NH3. It will damage the PM membrane. So we do need to have some battery storage system for power regeneration or power buffering and go through inverter and motor. So that's how I design the system. We do have the battery and with the DC-DC power converter to control power and manage them. And many of the fuel cell connect together in parallel to go through the battery energy storage. We don't need to have a single big fuel cell to do the job. Sometimes single big fuel cell could be expensive. For example, like talking about 50 kilowatt of the fuel cell would be really expensive, really difficult to handle. But instead, we can using a number of, say, 5 kilowatt fuel cell, maybe 10 kilowatt fuel cell, make up the total power. And then we connect all the fuel cell, full power electronic. So in this case, we don't need to only select a big fuel cell for the vehicle. Of course, we did energy management. How to manage them? For example, you can see that in a vehicle, there's many energy storage or many of the energy unit, including we got the battery, we got the bus voltage, how to control the battery, SOC of battery, state of charge of battery, and fuel cell, and the vehicle control unit. All of them need to have a really good energy storage system, energy management system. So here is one of the proposed work we're trying to install in a minibus. So this minibus is supposed to be 7 meters, 19 seats. So that's the design we are now working on. So we propose driving range about 500 kilometers. The motor power don't need to be too big, about 100 kW. This power level. So we try to store different type of fuel, roughly about 5 of the ammonia tank. We're able to fulfill 500 km of the requirement. So that means the actually operation is quite simple and easy. So this kind of minibus roughly about 7 tons, and the speed can go up to 90 kilometers per hour. So that's how the cracking technology we try to work on. So show you some samples. So basically we got ammonia stored in the liquefied version, and then through a cracker, purify, and buffer tank, and go to the fuel cell. So we are already conducted work in the laboratory. So that's the cracker. That cracker actually is really simple and high temperature. Use high temperature to crack the ammonia into hydrogen, and then that will pass through and go to our fuel cell. So basically, the operation is quite straightforward and simple. However, we check the documentation since nobody have done that using ammonia to power an electric vehicle. So supposedly, we are the first one to do in the world. So for the ammonia cracking technology, we do need to have some kind of the catalyst to help us to crack them. Otherwise, we need to really high temperature. We can lower the temperature using best catalyst to do the job. So we're working on many different types of the catalysts. For example, like one of the things we selecting will be iron oxide. The people may ask, would that be really expensive to crack them? No, it's not only furnace, high temperature, and also very low cost iron oxide, very cheap. We know that iron oxide very cheap material. So that means the whole thing will be really much same cost as a fuel cell vehicle. So we also do a lot of analysis for many different types of the catalysts. So there are different kind of sample, and actually many other research teams work on different kind of cracking technology, try to have best performance in terms of the percentage of cracking. So for example, like iron oxide can go up to 99.9, so really good. Other material, we can less than 50%. So we are now working on high performance cracking technology. So the whole thing development is shown in here. So we need to develop all the power control for each of the area. Each of the element, we do it with good confidence, but how to control them, how to manage them, how to make the energy flow will be best in terms of different kind of power level from the motor. So that's the job we have to work on. So here you can see all the components we've been using. For example, like we need to optimize the power level using maximum power point tracking and power converter, and also battery storage, and also different kind of the cracker and storage tank, and also flow meter, flow control, and also sorption, that's mainly to do the filtering. So we already installed them in small vehicle as to start the project. So here we run with ammonia and vehicle now we are working on. So we just like in the laboratory downstairs, if you do have time and go downstairs to see our development, is the first all electric vehicle based on ammonia gas. And so you can see the cracker will be here, the fuel cell behind, somewhere there. I think I do have a video to show you. Let me see if we can play it in here. I can play it just now, I'm not quite sure. Oh, this here, yeah. Is it, No, it's just already installed inside, but I'm not quite sure why it can't be played anyway. Anyway, so to conclude what we have done now, so we have developed ammonium-based fuel cell technology to power the EV. So basically, this small vehicle as a first demonstration, we successfully to demonstrate how to develop this technology. Our power level based on 300 watt. So that it will be good enough to power a golf car vehicle. So so this power level compared to our golf car motor, 3 kilowatt, but you can see that that's still able to power up because for a golf car, during the cruising, we don't need too much power. So that's why this power level will be good enough. We can also continuously to use the fuel cell to charge the battery. Use the ammonium fuel cell to charge the battery. Our energy storage, we still need a buffer. Just I mentioned, our buffer energy will be 5 kilowatt hour. So that would be really good enough. We continuously to use ammonia gas to charge the 5 kilowatt hour of the battery. So to conclude, you can see that we tend to use to promote aluminum for the fuel cell vehicle. Still be based on the PEM membrane of the fuel cell. So that's key or technology. And ammonium cracker, we need to know how to design them, how to optimize them. Also need to examine about the catalyst, what's the best catalyst we have to use. Also examine about the filtration, how to purify them, and also how to store the energy, many different stages of energy storage. And also optimize the power, including how to design a motor, supercapacitor, how to do all the energy management. You can see there's a lot of energy management needed to be there. And of course, we need to develop a sensor and protection in case any leakage, we are able to detect them. So that's it, what I'm trying to present to you. So to conclude, we can see that we require ammonia because we need a zero carbon fuel. So one of the good future you can consider safety operation, although slightly pollution, but they really small, a little bit of pollution, you can smell it. The good thing, you can smell it. So that means in case you leak, you can still know where they are. Really suitable for fuel cell technology. It's also alternative energy storage. Because as I mentioned, to compare hydrogen energy storage to ammonia do have a lot of advantage. So that's why we try to promote them. Fuel cell vehicle, we have difficulty only depend on the lithium-ion battery. We have difficulty only depend on hydrogen, but we are confident to depend on the ammonium fuel cell. Thank you so much.
Thank you, Professor Chen, for a very interesting and informative presentation. I'll save some of my questions and some of your others' questions later on. But I remember the days when I was a young engineer working for Air Product in the US. They have a very large ammonia plant in Louisiana and also one in the Long Beach, California. And every time I go down there, we got to go through very stringent safety training, right? You know, in case of a leak, you need to learn how to run like hell, and the plant is outdoor so that the leak will not do that much damage, you know, because it will kind of dilute it. So ammonia is a very interesting material, and we learned a lot today, and thank you very much. Again, would like to remind you that if you have questions for us, if you're online, you can type your question through the chat function of the Zoom program, and Rob, our consultant, will collect those questions and send it to me. And time-wise, I think we are doing very well. In fact, that we're only about 15 minutes behind, and those are primarily caused by the late start of the program rather than for other reasons, right? So I took the responsibility for that. Yes. 企喺度啊？ Oh, okay. All right. Well, the reason I tried to sit down was because I got the leg problem. In fact, I came here with a can, you know, right? But I'll try to do as much as possible. Can you see me now? Yeah. Okay. Now you can still see me, right? Okay. Now we are going to a younger speaker, and also a good friend of mine, someone that I really admire. That I was surprised when I first met him and his father, that a Hong Kong company, right, would actually at the leading edge of some process technology and a new material that might, you know, be a transforming technology for the new hydrogen era. So our third speaker is Mr. Albert Lau, who graduated at the age of 20 with a bachelor degree in material science and engineering and a minor in environmental engineering from Carnegie Mellon University in Pennsylvania, United States. Since graduation, he has returned to Hong Kong and worked extensively in the field of energy and environment, including work on silicon material synthesis, lithium-ion batteries, solid-state hydrogen, and photovoltaic and water treatment process. Albert is the co-inventor of several families of patents filed in major economies, countries, and regions. And before founding EPRO, Advanced Technology, Albert co-founded two manufacturing companies over a period of 16 years, serving as director and COO for both, and managing around 600 people across Hong Kong, China, and the United States. Albert also holds 11 Albert also holds a LLB degree from the University of London. So you can see this is a multi-talent young man, and I'm also proud that I am an advisor to his company, and he's going to talk about a new kind of clean off-grid mobile power supply. And some of you might be able to hear it first, you know, from our HAESCO seminar here. Robert, the floor is yours.
Thank you, Colin, for the flattering introduction. Hi. All right, still, it's a very good morning to everyone who is here on the floor and on Zoom from all over the world. So today, what I'm going to introduce to you or explain to you guys is a new off-grid solution, which I'm calling the off-grid solution. To give everyone some background on why off-grid solutions are important, off-grid solutions, actually, it will be better known as off-grid power, diesel gensets or solar powered or battery systems, whatever it is. The main purpose is to provide power. Unfortunately, a lot of us is quite misinformed in the sense of what off-grid power is and what damages it does to the world. For example, diesel generators, backup power, which is most government buildings or departments will have one in their buildings. For example, Hong Kong International Airport may have a couple megavolt MVA, well, probably around 20 or 25 MVA power generators. PolyU will certainly have them. Hong Kong government, the central headquarters will have them. It's everywhere. But these are the things that people don't really see because Hong Kong, we're in a very blessed land. We do not have much power outages other than maybe the super hurricane that struck a couple of years ago, which affected a very small part of Hong Kong. But other than that, why do we need backup generators? And what damages does it do? So if we look at other countries or regions, for example, Africa, Africa actually has 40% of its energy generated off-grid, which means mostly is by diesel generators. And diesel generators are exceptionally dirty. They are not like diesel combustion vehicles where it has all the catalytic converters to treat all the harmful gases that emits. It just goes directly out the chimney. And even that in Hong Kong, a lot of the backup diesel generators do not have much of the exhaust treatment. So it just goes up into atmosphere. So what can we do then? I'm going to introduce to you another concept of the energy system. I don't know whether any of you are familiar with this duck curve. This is the main problem of the current power system, as we know. The more renewable energy that we have installed, which the whole world is pushing, mainly on solar or wind off-grid or offshore wind or onshore wind, whatever that is. The more renewable energy we have, and since it is an intermittent energy source, we cannot actually control that. The more energy, the more renewable energy we have, the more risk that we have an overgeneration of. And for the grid, it needs to be always under balance. Otherwise, catastrophic events may happen, including blackout, load shedding, which means you shut down a certain portion of the grid, or rationing of the system, which is already happening in China right now. Well, people may ask, why do we have regeneration then? Well, the main reason is that we have what is called a baseload. Baseload is done by thermal, coal-fired power plants, or nuclear. That is usually what is being done. Otherwise, when we are in the evening times, we do not have sun. So what powers up our city? It's the traditional coal-fired power plants. That's why the G7 still did not commit to reducing any more coal-fired power plants by 2025 or 2030, just this G7 meeting. Well, when thermal generation and nuclear is still going to be on, which means renewable energies will actually cause more troubles to the grid. How are we going to balance that out? Well,
After solar, which is the easiest way for people to understand, when we are heading to late afternoon, the sun goes down. Everyone gets back home off work, and then it's called distributed energy use. That's where the power surge comes. How are we going to balance that? Currently, as far as I know, the best grid storage technology is pumped hydro. But pumped hydro, of course, everyone knows that it's limited by geographical locations, the season, whether it's a rainy season or dry season, whether you have enough water or too much water such that it cannot function. So this is actually a very big problem. So today, what I'm going to talk about, I'm not going to talk about the overgeneration risks. I'm actually going to talk about what ramp we need, which in another sense is the new off-grid power. So hydrogen economy, everyone has been talking about that since 2003, where George W. Bush, President of the United States, said, let's push hydrogen. But why are we at this day and age still hasn't progressed? We are still very much as we were back in 2003. Well, hydrogen is, of course, the envisioned future. It's clean, it doesn't emit any gases, it doesn't emit any bad things for the world upon use. I'm not going to talk about, again, what it means or the different processes of making hydrogen because of our previous speakers already introduced that. But why is hydrogen so hard, so difficult to be adopted by the world as the new source of energy? Because it's very small. It's the smallest known element in the world. As it's very small, it's very light, you cannot store it. And that's where we're stuck. The whole world has their, each major jurisdictions have their own country roadmap as to when hydrogen is going to be adopted. And most of them will say, we're going to spend another 10 years working on the different fundamental technologies to enable hydrogen economy, and then possibly up to 2050 or 2060 to say a full-fledged adoption of hydrogen. So what's the problem? So what I'm going to introduce to you is that something that I'll say to the younger crowd. It's like Avengers, right? Yes, we have developed the mini arc reactor in a cave. Well, not exactly a cave, but in a garage that we have started back in 2003. So what is silicon? Silicon is a very abundant element in the world. Well, of course, it exists as SiO2, which is better known as quartz or glass to others. You can find it anywhere. Silicon, we have found that it has actually two very important usages. First, it can be used as a new, the next generation lithium-ion battery anode material, or it can be used to generate hydrogen upon contact with a basic solution. However, what we have done for our silicon, which we're calling it Si Plus right now, is we have managed to incorporate nanopores into the material. As per different surface area characterization techniques, our average pore size is talking about 1 to 3 nanos, regardless of how large the particle is. So why is that important? Back in 2013, there was a first paper that published saying using nanosilicon to generate hydrogen on demand. When you put it into basic solution, it will generate hydrogen. But as we all know, nanoparticles are bad. You cannot pack it. It's very expensive to produce. And even if you produce it in bulk volume, you don't get much of a volume because it's nanoparticles. What we have done here is we have used traditional metallurgical techniques such that we can make this material in mass volumes, whether you're talking about 1,000 tons per day or even more. It's a basic foundry per se. I mean, I may be oversimplifying, but it really is a foundry. So with the particle that we have, this is an SEM. Of course, going to 1 to 3 nano pore size. To see a photo of that, you'll need a transition electron microscope, which I do not have that photo here. But this is what we have created. We have already obtained patents in US, EU, Japan, Korea, currently under review in China and Taiwan. So with major economies around the world granted, I would believe this is actually something novel. Well, I've also filed a couple other patents, which I'm not going to go over here. All right, so what is the material then? How does it work? So this is basic solution. Adding our silicon. Immediately hydrogen generates. Well, for those who are on the floor here, you may probably see there water vapor on the top. This is a very exothermic reaction, which is a very big difference as compared to magnesium hydrides or other forms of solid state hydrogen carriers, where you will need 200 or 300 degrees Celsius in order to release the hydrogen. We do not. So this clip is made in our lab, of course. Solid state silicon. You do not need any sort of protection. You can throw it in. You can open it up in atmospheric pressure, in open air, and nothing bad will happen. Submicron particles, even though, well, actually we are already testing 1 mm particles, which is huge in terms of, well, generating hydrogen for surface area dependent reaction kinetics. Solid state is very easy to pack, especially when we're talking about 1 mm particles. Well, lastly, the system can actually function at -10 or even to a maximum of -20 Celsius, up to 80 Celsius, which is pretty much anywhere that you can live around the world. 14% hydrogen capacity. We have already reached the theoretical limit of what silicon can actually do to oxidize water to generate hydrogen. So from as far as we know, we are the best hydrogen generating material there is known to Earth right now. So what does this all mean? What we're proposing right now, well, again, today's topic is the off-grid solution. We can actually build a scalable silicon plus based hydrogen genset. Hydrogen can be generated directly from Si+, as we have all seen in the previous slide. Hydrogen can be directly passed into a PEM fuel cell without any pressurization, any gas treatment systems, which is very different from alkaline electrolyzers, where still gas treatment is necessary. Otherwise, the PEM fuel cell, well, it will have very toxic consequences on the alkaline fuel cell. Well, in a PEM fuel cell, if the hydrogen is generated by alkaline electrolyzers. We already have a system in our factory in Hong Kong where a 150-liter reactor system can directly power up a 5 kW fuel cell system without any help. So what does this mean again? This means we do not need hydrogen storage tanks. Well, if you're familiar with how hydrogen stations are regarding their safety, their cost, well, costs, it's not even a question right now to me, because the hydrogen economy does not exist. When it does not exist, we do not talk about costs. Same thing like when we were talking about 30 or 35 years ago when the first mobile phone came out. Back then, it was the first phone cost maybe 20-some thousand Hong Kong dollars. People still bought it. When then the next Motorola came out and the phone was a couple $100, that was it. but people still bought it. It's not even about a price. It was about whether you can make hydrogen available. It's the chicken and the egg problem. The whole world only has 500 or so hydrogen refueling stations across the world. And people are only talking about, let's aim by 2025, we will have 10,000 of them across the world again. That means massive amounts of investments. And it takes a lot of time. When you don't have refueling structure, why are we even talking about hydrogen fuel cell vehicles? Who is going to buy it? No one. Which means it's a vicious cycle. It's getting nowhere. And that's the reason why we are still stuck since 2003, when George W. Bush said, let's push hydrogen. This genset is capable or will be capable of generating at least 1.5 megawatt hour per day. Simple reactors, fuel cell stacks, whether it's multiple stacks or one big one, it's more of a simple question for the fuel cell manufacturers to see which has the better efficiencies. We are going to couple it up with retired EV batteries. People ask, why retired? Why don't you use fresh ones? Well, half of me does batteries. So I would say rather I have some information, some knowledge on how batteries function. For retired EV batteries, it still functions perfectly. It still has about 70 to 80% of its capacity, original capacity. And since it has already serviced the whole lifetime of the EV, of the electric vehicle, it has proven itself safe. It doesn't auto-ignite, which happens to a couple of Teslas. It happens to many electric vehicles around the world. I believe last year in China alone, it had about 200 auto-ignition cases, and usually it came from one bad cell. It's not from many, not from 10 or 100 of the cells within the car. It's only from one cell that caused the auto-ignition of the whole car. And then it will get on the news, everything, and then bad things happen. So retired EV batteries, it's safe. It has surfaced at least 300 times or maybe even 500 times, depending on the cell chemistry. So it's perfectly safe. With batteries, it can sustain, it can support a very high power demand, which complements the fuel cells. Fuel cells, as we all know, it does not have power. It can run a marathon, but it cannot do a 100-meter dash. Batteries, on the other hand, actually complements the whole thing. That's the reason why we're coupling it all up. And then the usage, for right now, easiest for people to understand is off-grid EV charging. Charging infrastructure, grid infrastructure is a very, very, very expensive thing. That's why it's called infrastructure. It's not something that we purchase a chair and then pull it from IKEA and then bring it to the school or back to your home. Infrastructure is always expensive. Talking about cost. If we are going to use this genset, how does this compare in terms of, well, since we are talking about carbon neutrality, we are talking about economics. What does this really mean? For backup power, back to my first slide, talking about how Africa generates 40% of its energy off-grid. Even Hong Kong, I'm going to guess, has probably 1 gig-volt amp backup generators installed, which means even though it's not in active service, it actually is in active service because it's regulatory requirements. It needs to run average 2 to 3 hours per month, unfortunately, without being connected to the grid or to the power supply of the building, because it's just regulatory. It just needs to be confident that the generator works. However, another problem came with the New York hospital back in 2002, I remember. Hurricane Katrina. The hospital powered up its backup generators, but it actually did not work. Not because the generator did not work, because it was the plug, the connector between the generator and the building power supply. So with all these backup gensets around the world, does it really work? Yes, the machine does. But does it really connect? Actually, no one knows. if we're talking about a 4 MVA diesel genset, just maintaining the system itself without without actually generating used power, it burns about 18,000 liters of diesel just with one 4 MVA genset. I'm going to guess Hong Kong has 50 to 100 of those. That is just burnt diesel. That is CO2 that is not helping the world in any form or manner. But what if we change it with these gensets? Hydrogen gensets. Fuel cells are safe. It will always function as long as you don't poison the electrodes. Pass hydrogen in it, then it'll work. It does not have any moving parts. So you don't have any lubrication oil. You don't have the traditional maintenance issues with diesel gensets. So these are the things that the system can do. And likewise, if we are going to use this to power up the hydrogen economy, what can we do? We have effectively replaced the electrolyzer systems with our Silicon Plus, which generates hydrogen on demand. Again, we do not need grid infrastructure. Whereas huge electrolyzer systems, you would need huge cables, again, infrastructure to support. And when you're generating so much hydrogen by electrolyzers per se, no one will want that production center to be in the center of the city. So you probably need to be stationed somewhere outskirts of the city, which means you go back to the same problem of the original hydrogen economy, transportation and storage. So that does not solve anything. Power to X is a concept that the whole world is talking because there is no other grid storage material out there or no other grid storage technologies out there. That's why people are talking about power to X. But then no one actually talks about, so when you have hydrogen, how can you go back to store and transport? I mean, everyone kind of just leaves out and hides behind the veil and don't talk about it because it cannot be solved, unfortunately. The world has so much money right now that they don't care. As long as it's a sexy idea, people will throw money in. That's what it matters. But when we can solve the whole system of hydrogen from generation, distribution, storage, transportation, even to distribution, what does that really mean? This system, when we have our hydrogen source, we can couple with different compression systems depending on what local regulatory requirements are. People may say, I want the traditional high pressure storage tanks, compression systems, or I will want to go cryogenic where liquid hydrogen will be made. Both works because we have solved the hydrogen. We'll go back to air products where Colin worked before. We can go to Linde, we can go to all the different companies to purchase these systems, which means we are just a garment manufacturer. We buy the zipper from here, we buy the fabric from here, and then we put together the garment. And then that's it, because we have solved the most important of all, hydrogen. When we can put together a mobile hydrogen station, when we compare that with traditional hydrogen infrastructure costs. For example, in Japan, hydrogen station will cost up to 70 million Hong Kong because it needs to be earthquake proof. And that does not include any of the transportation logistics of hydrogen itself. This system for us, generators are very cost effective. These are just basic chemical reactors. Or of course, it needs to be gas leak proof. But otherwise, the main cost lies with the compression systems, which we buy, we couple it up, and then that becomes the hydrogen station. This should spearhead and leapfrog the whole hydrogen economy because we have made hydrogen accessible. All right. So we have talked about genset. What about SI Plus? What does it really mean? So SI Plus, if we pack the whole 20-foot container with SI Plus, This equates to 3 tons of hydrogen. If you use that hydrogen passed through PE and fuel cells, that equates to 60 megawatt hours. Or for those who doesn't really know what a kilowatt hour is, for example, our apartments in Hong Kong, usually the consumption per day, we're talking about 10 to 20 kilowatt hours. A full Tesla car, the largest one, the 100 model, has by its name 100 kilowatt hours. One container can give you 60 megawatt hour worth of electricity. That's what it means. Since the system is mobile, we have solved the dangerous goods, the flammability issues of traditional fossil fuels. Or even though diesel doesn't really burn, but then it's still considered a dangerous good. Our solid state material doesn't. It's solid state. It doesn't react to other, well, even if it's in contact with regular rainwater, surface water, it doesn't really react. It requires some sort of basic solution to help catalyze the system. So with this location on demand system, I would always use the analogy to say, let's go to do some fishing. We'll go to fish for whatever school of fish out there today. We drop our lines, waited for 3-4 hours. Hey, no fish bites. What can we do? We will move. Turn on the engine, we move to somewhere else. Hopefully we'll find fish. This is what it means, which is very, very, very different than traditional large-scale backup generators or off-grid power. We can move very easily. Containers. Low investment and maintenance costs because the system doesn't really have much moving parts as compared to diesel generators. Low carbon footprint, which I will continue to discuss on the next couple slides. What this system also means is that since we have fuel cells, byproduct is pure water. The system will support off-grid water supply, which again is not of concern with this conference. And the last one, when the whole world is talking about smart city, smart grid, Internet of Things, vehicle to grid, this system can support all of the above. I mean, I would go back and say, well, I'm not the Elon Musk caliber, well, hopefully soon, but Elon Musk has always talked about vehicle to grid. To me, that doesn't make much sense because the EV batteries is there to service the EV. It's not there to service the grid. You're just killing the batteries, and then you have more retired EV batteries that no one currently knows how to use it. Or there are some demonstration products in Sweden, in different parts of the world, using these retired EV batteries to power up a city. But mostly, it's only a demonstration scale. So EV batteries should support EVs and not the grid. But what we have, our system, since it already is using retired EV batteries, we're just providing a second life, gaining carbon credits, not to mention. We can actually support smart and microgrids, can combine with everything that you have per se, wind, solar, at different rooftops, or even the peak and trough of the grid system, that these are all the off-grid systems that can support and balance the grid. How do we compare with different solutions? First one is our 12 hours. It's continuous output. We do not need to take the container or the system back to anywhere to recharge the system until the cartridge is used up. Again, each 20-foot container can provide up to 3 tons worth of hydrogen or 60 megawatt hours. Until that is used up, then we'll have to replace that cartridge. But not the genset. The genset can stay anywhere it wants to. Well, other comparisons. Porsche has a system, 2.1 megawatt hour worth of battery systems. that charges at their own facilities and then pull up to anywhere that their clients wants as an off-grid EV chargers. Well, main problem is, of course, it takes a long time to charge 2.1 megawatt hour worth of batteries. It requires infrastructure. Again, they need to drive back and forth. It's just the cons of the system. Toyota has a fuel cell truck, has hydrogen tanks, which again, hydrogen tanks only carries about 5% of its own weight of the actual hydrogen fuel in pressurized form, not in liquid form. So this truck will deliver about 612 kilowatt hours until it needs to go back to hydrogen refueling infrastructure. Again, infrastructure. When you don't have hydrogen, this truck does not work. Of course, lastly, which everyone should be more familiar with, is off-grid solar. Couple that with batteries, and then you charge up the batteries. When cars come battery to battery, which means it's DC to DC, it's very simple. Very straightforward. Problem is, what if there's no sun? What if it's a rainy day? Then too bad you cannot charge your car. You may need to wait till tomorrow or a couple days later when you see the sun again. If your car, unfortunately, in the bad event of running out of electricity. All right, so since HAESCO, we're talking about carbon neutrality. We're talking about how sustainable we are. This is an LCA analysis I've done with my collaborators at City University of Hong Kong. This is what our system is. For silicon, if we are producing by renewable sources, which is, here with the wind, we are talking about between 10 to 15 kilograms of CO2e per kilogram of hydrogen. What does this mean? You can compare with different forms of hydrogen generation, whether it's SMR, steam methane reforming, by pure electrolysis, or other formats of hydrogen generation. We're actually, I would not say we're the best, but we're certainly not the worst either. And don't forget, we have solved the hydrogen generation, we have solved storage, transportation, and distribution. So this is all in one package, as compared to everyone else just talking about how much carbon do we emit in generating our hydrogen. As Professor C.C. Chen, academician, or better known as agent father of EVs, he has always said, think holistically. Don't just talk about one thing because you don't see the full picture. And for this, I will say we're trying our best to look holistically to see what system within the whole supply chain of the hydrogen economy have we missed. This is what we have come up with. So this is how we compare. So I would dare the world to believe, to fight for new technologies, because we're talking about energy. It's definitely going to be a hard fight. Who is going to lead these technologies forward? No one wants to take risks, especially large companies or governments. Well, now may be different because the whole world is talking about carbon neutral by 2050 or 2060. Well, the last thing is I dare everyone, let's change the world together. And by that concludes my presentation.
Thank you, Albert. I heard quite a few of them. And I'm still learning something new, which is good. And you and your team continue to innovate and continue to ask questions, trying to refine what you're trying to do. conclusion of the hydrogen era. As we see in a very short 2 hours with 3 speakers, hydrogen era is definitely going to come. But how and when is still a question. There are still a lot of competing technology system, right? Moving lab, moving for proof of concept, commercial application is still required. Like Professor C.C. Chen have said, right? It's a complicated process, and it takes time, and it will cost. As the moderator of this seminar, I have a few announcements to make. The next seminar is going to be on 7 August 2021, and the title will be In What Way the Power Low Carbon 2050 target will affect the manufacturing industry. So please watch out, right, for its announcement and registration through your email. I have a very good news for some of you that attend this seminar and wonder how you can be a member of HAESCO. There will be an open enrollment period coming up, which you or your company can join with your first year membership fees waived, free of charge. And the board have made that decision so that we can have more people interested in energy efficiency and interested in the goals and objectives of HAESCO to become a member and participate, right, in many of those activities we have been doing in the last 4 years. But more importantly, because that our visibility, right, with especially Hong Kong and the Great Bay Area authorities, we've been seek out for a opinion, policy advisors, or idea, right, so that more member we have, we'll be able to be the channel, you know, of those members, right, for those things. Now, once we close that open enrollment window in the future, joining the HAESCO will cost you Hong Kong $500 a year for individual members and Hong Kong dollars 1,000 for a company. So even you have to pay, it's not that much. But the good news is that coming up, there will be a window of opportunity or enrollment opportunity to join HAESCO free of charge. Especially for those who attend this seminar and want to have a continuing education certificate or credit, you need to fill out the questionnaire that was sent to you in the confirmation of your registration for the seminar. So that's very important. And lastly, I also want to take this opportunity to thank you for the organizing team for this seminar, which are, you know, Rob Chen, who's our consultant, and he organized and handled all the technical connection for this seminar. If you see him walk around and try to adjust the volume of the voice or the connection, he's the guy. I want to thank you, Ricky Lau, who's also our HAESCO board member and a data scientist. He has been one of our very active, you know, member helping organizing seminars and other activities. So thank you. But the largest, you know, thanks go to Amanda Shun. She is the project manager for this event and for future OSI events. She's also working with our honorary treasurer as an assistant treasurer of HAESCO. So will you all join me to give this team a big round of applause? Now, let's move on to the panel discussions. I have collected quite a few questions here that were sent to us. But before I ask those questions, can I invite Professor Chen and Albert to come to the front so that people online can see you through the camera of Zoom? Huh? Okay. Yeah. Actually, it's not that important that I'll be in the view of the camera. The speaker is more important. Okay, the first question is for Professor Chen. Nitrous oxide is also one of the greenhouse gases. How should it be processed during the production of hydrogen from ammonia?
Well, that's a really good question. So when we crack the NH3, actually in our catalyst system, we do not see the nitrous oxide. We can crack it really well with only the side product, only nitrogen. So the nitrogen, when you go to the fuel cell, it doesn't bother the fuel cell. So the performance of fuel cell is really good. So we don't have any problem of nitrous oxide.
Thank you. The next question maybe it will be for all three speakers. Are there any hydrogen application in Hong Kong now? I would maybe also extend it to Hong Kong and the Great Bay Area. And since the professor sat next to me, I'll start with him and then go to the other speakers.
Actually, I think the hydrogen economy is still starting in Hong Kong. I know government is trying to talk about that. We have a lot of new projects, even though new initiative for this hydrogen economy. But I think for the commercial development at the moment, especially for electric vehicle side, will be really limited. And even though for the building application, I do not see any large project at the moment. So I think we're starting. I think there will be a really good opportunity in the near future. I know a few companies trying to develop some hydrogen generation plant in Hong Kong or maybe in Great Bay Area. I think in Great Bay Area, I think we do see a lot of projects working on starting to develop the hydrogen economy. And perhaps, Albert, you can help me to answer that.
Thank you. All right, so for my company, we are already in contact with a few Hong Kong departments or agencies, which I'll keep confidential, to work out different trial projects with what our system can offer, whether it's being backup diesel gensets or hydrogen gensets or as a novel hydrogen refueling station. So we're also in contact with EMSD, with Fire Services, with Policy Innovation and Coordination Office to enable new regulations, policies, international standards can be applied to Hong Kong. So that's my part.
Claire, are you with us?
Yeah. So in terms of Greater Bay Area,
Claire, are you with us?
Yeah. Can you hear me and see me okay?
Can you hear us?
Yeah. Can you guys hear me?
Huh?
Can the host unmute me? Can you guys hear me okay? Hello? Can you guys hear me okay? Hello?
We hear you, but I think they can't hear you.
Yes, please.
Okay, you can hear me now?
Yes, yes, please.
Okay, cool. I mean, the two speakers have talked about the hydrogen applications in Hong Kong, so I'll talk a bit about the applications in Guangdong. So the city of Foshan has a very aggressive goals and policies to support the hydrogen applications. So currently there are 24 refilling stations in Foshan, and there are over 400 logistical vehicles that fueled by hydrogen. Yeah, so that's the development. However, there's not much like hydrogen as a byproduct or cheap hydrogen production in Foshan. So the future growth will still depends on the production cost. Yeah, thanks.
From the online audience, any questions from the people here? Sarah?
Thanks, Colin. I was really interested in all of the presentations. Hi, Luan, excellent job there. But I was particularly interested in the last one with the silicon, because I'm on the board of a generating company in the Philippines, which is looking to start building off-grid generators. And by off-grid, I mean real off-grid, not like in the basement here. I mean up in the mountains where there's absolutely no infrastructure. So my first question to you is, where are you in your timing of your development of this? You know, how quickly are you actually going to want customers like potentially my company to actually say, yep, we're ready, you know, give us our silicon canisters and you know, how soon do you think your entire system will be ready to get out there and start supporting the off-grid community?
Thank you for your question. Our timeline, we're looking at approximately in 9 months' time, we will have a prototype that can directly power up a 5, even up to 10 kW fuel cell system, coupled with X amount of retired EV batteries, which is actually a very simple function of adding in more retired EV batteries into the system. So in that regards, all the research work has already been done. It's just what remains is the development of the system, which again, why I'm quoting 9 months is because COVID pandemic is affecting all the cross-border communication and transport, such that it really delays everything.
Thank you, Albert. And thank you, Sarah, for asking the question. By the way, for those who don't know Sarah, she's a former partner of the Lantau Group, and she's also very active, you know, in the energy related consulting area. And you're not consulting anymore, but she would love to be as an independent board member of your company to provide advices that way. But what I want to say is that if you want to get involved in some more interactive meetings, you know, right? Both HAESCO and IPPF, which I'm also the chairman of, conduct, you know, monthly Zoom meetings. And Sarah happened to coordinate one of the IPP Zoom meetings, you know, right? Both, you know, on a regular Zoom monthly meeting, as well as the Hydrogen Committee monthly meeting. HAESCO also have a OLL, online lunch and learn, a Zoom meeting every month. So especially if you become a member, you'll be on the mailing list for that, where you will be able to participate in a Zoom meeting, unlike the webinar, be able to ask questions, and we have people that are knowledgeable in the industry to share idea, you know, and news among themselves. I got another question here.
Yes, hi. Thank you, Colin. My name is Robert Liu. I'm with HIW Private Equity. And thank you very much for to the speakers and the organizers for the forum. And I have a few questions. Maybe I'll say them all now. First one is about the technology status of solid oxide electrolysis. And maybe this is for Li Yuan, since you were talking about the different costs, cost comparison of different kinds of hydrogen generation. Yeah. Second question is about the technology status of using ammonia as the energy form. Maybe this is for Professor Zhang. And then about the SI material, that's very, very interesting. And how should we look at it? We know that it's a kind of energy form. It's a form of energy carrier, and normally it's hydrogen, it's natural gas, but now it's a material. So how should we look at this? And then the status. I think Sarah already asked that. Yeah.
Thank you, Robert, for asking the question. Robert is the CEO of the Invesco Wanang Fund, and he was an investment banker. During his younger days, he helped me with project finance of some very large power projects in China. So thank you for joining us today. Who wants to answer the question first?
Perhaps I can answer the question about the ammonia first. Actually, the ammonia as a carrier for the hydrogen is quite, have a lot of the research has been done. It actually have a lot of application now. So for example, like in England, we have been building kind of the energy storage system using ammonia. Mainly the input will be like the solar power or wind power, and the energy will store in terms of ammonia. So how they get the ammonia mainly is to combine nitrogen and hydrogen become ammonia. So this is one of the way we can store the hydrogen, but now using ammonia. So we quite like to use ammonia as the energy storage because, as I mentioned just now, the pressure using is quite much lower than hydrogen. We don't need to use 700 bar. We only using 10 bar or 8 bar. We can liquefy them quite easily. We can transport them quite easily as well. And also per unit volume, the energy content will be much higher. So there's a lot of work has been doing as ammonia storage. Of course, for the vehicle, there's a no material has been seen. So we are now the first one trying to install them in vehicle. So it's quite a successful case. But so that means for vehicle is the first time we do the job, but for ammonia at the hydrogen carrier would be, I think a lot of the work has been done.
All right, I'll go back to Robert's question before I forget. So what I see SI Plus going forward is, of course, I will hope that it becomes a commodity. In my presentation about the duck curve, we talked only about the virtual power plant, the backup generators during this presentation, but the other part is actually demand response. Demand response is actually a system that our technologies can actually cope with. For example, just some extra information. IRENA, International Renewable Energy Association or something like that, they said worldwide about 90+% of the offshore wind renewable potentials has not been exploited. Why has it not been exploited? Because the grid needs to be in constant balance. Even though you have all these electricity generated, no one's going to use it. But at least the demand does not match the supplies. What our system can actually do, what our technologies can support is to serve as the grid storage material that can finally be distributed for different purposes, whether you want to fuel up a battery EV or hydrogen EV or backup generators, whatever that is. So on the other question, oh, sorry. Brilliant. That's actually a question from the forum too. The reaction right now is primarily with water. We have added in sodium hydroxide as a catalyst. What then becomes is sodium silicate, which is a very prominent building material, or actually for everyone who cooks or have eggs at home, then you will be in touch with sodium silicates, because all the eggs at our homes in our fridge has a surface layer of sodium silicate to protect it from rotting soon or faster. The other hand is we can change the sodium silicate to calcium silicate, which is what Bill Gates in his How to Avoid the Climate Disaster is coining a term as green cement. That is what we can do. Well, sorry, one more question. Where is the CO2 coming from? So our whole LCA analysis, of course, we're including from the whole process of the system, meaning we are starting from SiO2. The CO2 comes from the reduction of the quartz. So SiO2 plus carbon becomes Si plus CO/CO2. So that's where the carbon or CO2 emission comes from. It's a foundry. Yeah, I have kind of roughly sketched out on back of the envelope a 6,000 ton silicon production per day system.
Online can also hear. Sorry about that. It's a limitation of our...
Thank you. My name is Darren Fenton from Doosan. I just wanted to ask about the scalability in terms of the instantaneous usage of the SI, as well as how much you can produce. Is there a limitation on how much you can allow to react at a time? Is there any, have you looked at any large scale uses for the hydrogen generation at the moment?
Thank you for your question. Well, we have already done quite a bit of the research on our end. What remains is just the development of the systems. Scaling the system, because it's a chemical reaction, it's actually rather simple. I mean, chemistry, it's not, well, the material itself is very new, but the chemical reaction is very old. So all the rate equations, kinetics, everything, it's not super difficult. It's not rocket science. So scalability is rather easy. Big usages from what I see right now is actually to power up the marine sector, where heavy fuel oil will be phased out by 2023 from the IMO. They are looking for new sources of energy to power up marine or their cargo ships. LNG, well, people are trying to push it because that's the next best thing available. But what I see as the main problem, the obstacle for pushing LNG, is that you need infrastructure again. Not all the ports have LNG infrastructure, which means you cannot refuel your boat at all the ports around the world. But if we are going to use silicon, it's just filled in containers, plug it in your boat, which is similar to a cartridge within our printers, then the system will operate itself. So a little bit more information, for example, 1 ton chemical reactor that will be able to generate about 60 to 80 kilos of hydrogen per day. So that's the scalability of the system at the moment. We're still trying to well, on that note, we're still developing more efficient systems internally.
I believe there is a question for Leon, right?
Yeah, I'm going to answer Robert. So you just asked a question about the solid oxide.
Yeah.
Electrolyte.
Kurt, did you hear that question? Or you need the
Yeah,
question to be repeated?
My understanding is that Robert wants to know more about the solid oxide electrolysis. Is that right?
Yes, we can hear you.
Yeah, cool. So just to talk more about this kind of electrolysis cell. So it's the advantage is that it can have very high energy intensity, and the commercial efficiency is over 90%. And it's also more environmental friendly compared to other electrolysis. And at this stage, it's relatively higher cost. And we have seen some case in Germany where they use the renewable power to make and use the solid oxide electrolysis cell to produce hydrogen, and the capacity is 720 kilowatts. Yeah.
What do you view as the key constraints in current hydrogen supply chain? What view do you have on the regional production of green hydrogen in the future? I guess that's a question for all three speakers. Professor, you want to start?
Conventionally, we try to produce hydrogen. There's a many ways we can do that. For example, like a lot of the carbohydrate, we can crack them and produce the hydrogen. And we can usually to use the electrolysis to produce hydrogen from the water. So I think existingly, there's a lot of the method has been using quite successfully for producing the hydrogen. And so there will be a lot of way, like Albert has proposed some new way for doing that. Maybe I pass the mic to Albert.
Thank you. My views on green hydrogen, I will use an analogy is that, yes, you have learned how to play piano for 1 or 2 years, and then you ask me how can I play Rachmaninoff III or Tchaikovsky piano concerto. That's pretty much the same analogy. Why do we need to play such a hard standard or such a hard piece when you have just first learnt the skill? Green hydrogen is the vision. That's where the world wants to be in 30 years' time, not now. When we keep on talking about green hydrogen, green hydrogen, green hydrogen, we will be stuck here talking again about green hydrogen in 20 years because nothing will have progressed. Things will only stay as good as it is on paper. It will not get better because people still keep on talking about green hydrogen. What green is? Well, every country/region has their own definitions. For that part, I've done some research on it. US has their definition, France, Germany, rest of EU, China, Japan, every country has their own definition of what green is, whether it's produced at source using green energy or delivered using a lower amount of energy, etc., etc. So there isn't even a clear definition of what green is, other than, all right, you use green energy. But for if you're talking about the silicon, our technology SI+, our system can actually use curtailed electricity. And when we're talking about curtailed electricity, look at the wind farms across the world. The largest wind farm is in Gansu. And as far as I know, the underutilization rate is about 40%, maybe something less, but that's huge. That's curtailed. If the grid wants to use more renewable energy, which means it's the renewable energy penetration, then the traditional coal-fired power plants will need to be curtailed or actually be lowered in their capacities. That's what's happening in China right now, which is causing the rationing of electricity. So to me, it's a question of how you define different colors of hydrogen. And back to Robert's question, the silicon has defined a new breed of energy. It's not exactly hydrogen. So how am I supposed to describe what the hydrogen generated from our silicon is? It's a completely new breed. So you can call it the alien.
Claire, you want to comment on that question also?
So just to make sure I understand your question, so you're asking the key constraints in the hydrogen. Is that what you want? Colin, am I understanding your question correct? Can I hear you, Colin?
The question is, what do you view as key constraints in current hydrogen supply chain?
Cool.
What view do you have on the regional production of green hydrogen in the future?
Sure. Yeah, so I will share a bit from the policy perspective, because currently we say that the hydrogen is lacking more economy of scale, or lacking more production to decrease its cost. And actually there's some coordination along the supply chain is needed. And this coordination may not automatically happen from bottom up from the markets. So that's why we see that different governments, no matter national or provincial, are doing something like blueprints or like hydrogen strategy, so that to make sure that when there are electrolysis production is encouraged, and at the same time the refueling station is encouraged as well, so that we see that, for instance, in Beijing, they have a target that to build more fuel cell electric vehicles, like 3,000 by 2023, and 37 refueling stations by 2023 as well, just during the Winter Olympic. So that's why I think the policy of the promotion is a key constraint. How supportive it is for the hydrogen supply chain. Yeah, thanks.
I think we probably only have time for 2 more questions. I'll ask this one first. I will come to you, Sarah. You will be last question. The second last question is, how will hydrogen compete with batteries for achieving the net zero target? So I guess it's how hydrogen is compared with the current favor of the day, which is battery, in helping us achieving the net zero target. And again, because the professor sit next to me, so he got the first crack.
Yeah. So there's a lot of discussion on this area. You can see that most of battery, for example, like lithium iron phosphate battery or LTO battery, the efficiency from electrical to electrical really, really high. Something like 99% is quite common. But you can see that if you want to use hydrogen as the energy storage, firstly, you've got electricity. How we can produce hydrogen, one thing, for example, like electrolysis, then efficiency for electrolysis is not very good. I think something like from 50 to 80% would be reasonable. And after you have the hydrogen, and then you want to return back to electricity, then you use fuel cell, hydrogen fuel cell. The efficiency is something like 40 to 60%. So actually, the overall efficiency, combine them using hydrogen as an energy storage, you're talking about, say, 30% would be quite a good number. Compared to the battery itself, will be 99. So that's obviously for the near term, we quite like to use battery. But of course, we know that for the longer term, battery have an issue mainly about how to recycle them. At the moment, most of the lithium iron phosphate battery or other NMC battery, we are impossible to recycle them. Because if you recycle them, the cost will be at least 5 times to 10 times higher than the manufacturing. So that's why it comes to a problem. We don't know what to do. So if you want to have short-term solution, use battery because it's really good efficiency. But long-term, we do need to develop some other battery type of technology, have high efficiency easy to recycle them. But of course, hydrogen will be another way we can process the energy as an energy storage.
Thank you. My take on how batteries versus hydrogen, how this fight will become. To me, it's left and right hand. Or if you look at it from another analogy as a rocket going from Earth to space. It's different propellants that we're talking about. It's not apples to apples. It's apples to orange. It's a question of how we put the technology, we put that energy to use. For battery EVs, it will win in several occasions. For hydrogen, again, it will win on other occasions. So for example, let's go back to marine purposes. Battery boats will never work. Well, I'm talking about huge boats, not the simple ones that we would go up, like 10 or 20 foot small boats. But when we're talking about huge ones, that will never work. Because again, if you go to the port, you need to charge up the whole boat, whether it's a couple gigawatt hours worth of electricity, then the grid infrastructure, the downtime that it will require to charge up the batteries, it will never work. Hydrogen, on the other hand, plug it in, then it goes back to the PV equals nRT problem of ideal gas law. You depressurize the original hydrogen storage tanks, purge it into refueling the tanks on board, then that downtime will be a lot shorter. So to me, it's not a question of who wins. It's a question of how they marry. It's perfect. They should be perfectly complementary to each other. That's how I see.
Kara?
Yeah, I think I agree with Albert. So yeah, just to save time. Yeah, I just said I agreeing with Albert. Just to save time, we can move to next question.
Hi, thanks. Sorry, it's another one to Albert. You started your presentation by talking about diesel systems, but you never really got to the punchline, which was that if I was to take out a diesel system up in the mountains of the Philippines and replace it with your system, what would be the difference in the cost of the generated electricity from the consumers up there? Assuming I'm doing this in, say, a year or two's time when you've got things, properly running.
If I'm not mistaken, diesel, 0.4 liters of diesel would generate 1 kilowatt hour, if I'm not mistaken. If we're using that amount, just talking about regular diesel, not biodiesel. Regular diesel, the cost of per kilowatt hour, we would be on par with diesel. But the good thing is we generate pure water. And maintenance will be a lot less. We don't need to change lubrication oils because it's not much of a moving part within the system.
Okay, with that, we concluded today's seminar. I think we are about on time. I want you to join me for a big round of applause for our three speakers. And I also want you to give ourselves a big round of applause for spending a variable Saturday morning or Friday evening for those who are from North America for this event. On behalf of HAESCO, we thank you. A quick reminder, open enrollment period is coming up, so make use of it to become a member. Our next, for those who attended the seminar this time, we will send it through your email systems. And for those who are, for those who are here at the site, you can pick up an application form right away. for those who attend our seminars in the past, we have on your record your email address. We will send that to you as well. Also, a quick reminder, the next seminar that's sponsored by OSI will be on the 7th of August. So thank you again and have a good afternoon.